Okay. And can you all see that?
Yes.
Okay, great. So I am going to be talking today, the title of my talk is Selective Inference, or Why a Division of Nephrology should care about P. And I'm sorry to say that the P in question is not urine, but rather p-values. So, but I hope you will indulge me in that. So a brief outline of the talk. I'll spend a few minutes talking about the reproducibility crisis in science, give a brief refresher about p-values, and finally give an illustration of how selective inference might be contributing to the reproducibility crisis. So we might start off by saying, is there a reproducibility crisis? And this survey of over 1,500 researchers that appeared in Nature in 2016 would seem to indicate that there is. So 52% of respondents in the survey said, yes, there is a significant crisis. And another 38% said, yes, there's a slight crisis. So overall, 90% of respondents said that there was some sort of crisis of reproducibility. And for those who are unclear, by reproducibility, I simply mean, can you reproduce another scientist's or even your own experiments or research? Moreover, they broke it down by field. And in medicine, about half of respondents said that 50% or less of published work in our field is reproducible, which is striking. They further went on and asked, okay, what factors are contributing to this irreproducible research? And the top rated factors were selective reporting, pressure to publish, and statistical design and analysis, cited as always or often contributing to the problem. So finally, respondents were asked, okay, what could help? What could boost reproducibility? And the top answers dealt with statistics and teaching, with roughly half of respondents saying that a better understanding of statistics was very likely to boost reproducibility. So I'm here this morning to give you a teaching talk about statistics. Got the thumbs up from Matt, so that's good. Okay, so a more recent white paper by Yoav Benjamini in the Harvard Data Science Review on this problem parsed the causes of the reproducibility crisis into two categories, what he called non-evident and evident causes. So non-evident causes are those that are not necessarily apparent from reading a published manuscript. So for example, that might include publication bias, the fact that editors and reviewers tend to look more favorably on results that are statistically significant. The flip side of that is the file drawer problem. The fact that researchers themselves may be less interested in or have trouble publishing non-significant results. And you've probably heard the derogatory term p-hacking, which just refers to analyzing data in multiple ways and tending to select the analysis that yields the most pleasing of results for publication. So contrast those causes with what Benjamini calls evident causes, which are those that you might actually be able to observe in the published manuscript, which I thought was an interesting way of framing this question. So, for example, he cites as one of these causes a presentation of only significant results in the abstract or in the main text of the paper and relegating everything else you did to the supplemental tables that maybe nobody's going to look at. Another possible cause are pre-screening of exposures, say by doing univariate analyses with the outcome prior to a final model, or in general, model selection, where you're choosing exposures in the models of interest based on observed data. So for the rest of this talk, I'm going to have a pretty narrow focus. You know, as statisticians, I'm limited in what I can control, but a narrow focus on those last two evidence sources, which are examples of what's sometimes called selective inference. Okay, so we'll give a little example. So let's say that my objective is to investigate the association of a new instrument called the LZQOSL with EGFR among 1,000 patients with CKD. So this LZQOSL is a 100-item instrument. In the purpose of time, I've only given you the top 3. So questions include, on a scale of 0 to 10, how much do you enjoy talks about p-values? On a scale of 0 to 10, how much do you enjoy doing power calculations? And on a scale of 0 to 10, what proportion of your time is spent thinking about statistics? So clearly, this is made up. Clearly, I have just simulated this for the purposes of this talk. And clearly, there's no association between this made-up instrument and EGFR. Okay, so that's the point. And so if I were to, say, simulate some data and look at a scatter plot of these, okay, you would see no association, no true association between, say, item 1 on this made-up scale and EGFR. The true slope is 0, but in sample, from sample to sample, the slope, the estimated slope, is not going to be exactly 0. Okay, so here the slope is 0.12. Here the slope is slightly negative, here the slope is slightly negative, and so forth. Every time, I would be very unlikely to get a slope that is exactly 0. All right. So if you think about plotting a histogram or a density of those slopes over many, many samples, you would see and expect and see that the center of that, on average, the slopes you would see would be 0. And that there's some variability around that, okay? But mostly pretty close to 0. Once in a while, you'll get kind of a weird one. Those are the tails. But most often, it's close to 0 if the true slope really is 0, if there's really no association. So let's suppose that you took a sample and got a negative slope. So I've shown that here. I don't know, can you see my, my cursor? You can,
Yes.
okay, great. So let's say I got a negative slope shown by this solid black line, all right? Then the p-value, the definition of the p-value is the probability of getting something as or more extreme than that, assuming that the true slope is 0. So in this case, 8% of the area falls to the left of that line, and symmetrically, 8% falls more extreme in the other direction. So in this circumstance, the p-value would be 0.16. All right, that's all a p-value is. Now, sometimes you will get an extreme slope just by chance. Okay, that might make you think that there was an association. Even though I simulated this data, I know that there isn't. Okay, so by convention, we draw a line in the sand, which I've shown by these dotted red lines, to say, okay, if we get a slope that's more extreme than this, we will say there's an association. Okay, we'll conclude that there's, you know, significant evidence, blah, 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 reject the null hypothesis. Okay, and that line in the sand is designed so that the probability of getting something more extreme is exactly 0.05. That's where this kind of like magical 0.05 thing comes from. Okay, so we have to have some level of evidence where we're going to reject the null hypothesis. By convention, that happens to be 5%. Okay. So formally speaking, we call that a type 1 error, or I'll sort of interchangeably call it a false positive. So the false positive rate is the probability of rejecting the null hypothesis given that that null hypothesis is true, which I know it is because I generated this data. So in my example, that's the probability of declaring that this instrument and EGFR are related when in fact they are not. Something probably closer to home for you would be, say, the probability of carrying forward an ineffective treatment from a randomized clinical trial, or say the probability of declaring that a biomarker is prognostic when it's actually unrelated to disease. Okay. If we're using this 5% threshold, then that should occur 5% of the time under the null hypothesis. Okay, if the inference is appropriate. And I'm here to claim and try to convince you that the false positive rate should be what we expect. It should be 5%. Okay, now why that sounds like a tautology, but I'm going to try and convince you that it's not. And I'm similarly going to try and convince you that it actually is very important to inference that the false positive rate should be what we expect. So imagine if you thought you were only carrying forward 5% of ineffective treatments in the RCT setting, but in fact, you were actually carrying forward 20 or 30%. That would be a very big deal, you know, both as a researcher, as a statistician, as a provider, and as a consumer of, you know, say drugs, for example. So I, through simulation, have generated a little series of cases to illustrate how this might be imperiled by decisions about analysis and when it's not, for example. So our goal here is to investigate the association of my LZ QOSL with EGFR. I've already told you there's no relationship. So I simulated data for 1,000 people on this 100 item instrument where there's no true association with the outcome, EGFR, and I did that 5,000 times. Okay, so I can look at what happens over if I were to take samples over and over and over again. That's the advantage of simulation. And I'm going to look at 3 different analytic approaches. So case 1 is to report only the association of item 1 with EGFR. So this is the setting where I have a pre-specified hypothesis. Okay, so, oops, okay, so here is what happened in my simulation. So let me orient you here. So I've gone from showing you slopes to showing you test statistics, but you can kind of think of it as on a similar scale. So this black line is showing the density that we expect under normal sort of rules of inference. The red dotted lines, again, are showing our line in the sand that we said anything beyond those lines, if we got something beyond those lines, we would declare there to be an association, we would declare it significant. And I'm telling you that in this analysis plan and under this data generating mechanism of the null hypothesis, no association, that 248 out of my 5,000 simulations, in that many, I rejected the null hypothesis. So 0.0496% or 0.0496 proportion of replicates, I rejected the null hypothesis. That means that the false positive rate was exactly 5%. Okay, that is exactly what we wanted. All right, inference is working, that's great. Okay, let's go to case 2 then. So in case 2, suppose now instead of only looking at item 1, I'm going to look at all 100 exposures separately and then only report the association for the most significant one. Right? So same thing, I'm going to look at my what the test statistic was. Okay, again, this nice normal distribution shows me what I expect to see. And the dotted red lines are showing my line in the sand that I'm going to declare anything beyond that significant. But because of this inference procedure that I have told you I'm going to do, I'm going to look at the most exciting one and then report that one, that almost every time I got something that was exciting because I selected for that. In fact, I got something exciting, something significant over 99% of the time. Okay, so I looked at 100 tests. Maybe that's not surprising to you, but what that means is that the false positive rate was 99%, when nominally I thought it was 5%, or I said I was only going to carry forward 5% of null associations, but under this analysis plan, it's really 99%. That's pretty awful. Okay, so we've gone 15 minutes here. You said, okay, I'm tired of thinking about statistics, Leila. Okay, multiple comparisons are bad. I'm not going to do that anymore, but instead, how about I do some model selection? Okay, I'm going to let the data tell me which ones are most strongly associated, and then I'm just going to fit one model. Okay, you told me that was good, right? So in this scenario, I'm going to use the lasso, which you may be familiar with as a tool for model selection, for reducing the number of variables in a model to select one final analytic model. And then I'm going to look and see, does that model explain EGFR? Okay, we know that none of these variables are really related to EGFR, so they should not explain EGFR, just to reiterate. All right. So it's a little bit better than just selecting the top one, but unfortunately, it's still not good. Okay, the lasso chose the null model or the correct model 41% of the time in my simulations, but 59% of the time it chose at least one exposure as being significantly related to EGFR, and almost all of those models said, yeah, this subset of exposures is related to EGFR, which again, we know is not true. And in fact, on average, those 59% of models chose 6 exposures on average. So the false positive here, in fact, is 58%. So again, we thought we had a false positive rate of 5%, but under this analysis plan, which on face value, it looked like you were just fitting one model, is really 58% and still awful. Another way of saying this is that in both of these cases, the selective inference process produced p-values that are too small. The evidence seems very compelling, but it's because you actually have selected for the most impressive results, the most impressive exposure or the most impressive model. All right, so hopefully I've convinced you that yes, this is a problem. The next question is, okay, how can we fix it? Well, there are a number of different approaches, and this talk is not long enough to go into great detail of any of these, but I will just put these out there and talk a little bit about how they might help. So first of all is case one of just having a pre-specified hypothesis or having what they sometimes call hierarchical analyses. So think about the randomized clinical trial world of you have one, possibly two pre-specified primary outcomes where you're going to hang your hat on that. And you can look at other outcomes, but they are considered to be more exploratory. And if you saw something significant, that would not necessarily be definitive for you. So we saw in case one that, yes, that still controls the false positive rate at the appropriate level. The second possibility is to sort of control multiple comparisons, say by using like a Bonferroni correction. So for those of you, I think probably most people know, but a Bonferroni correction says, okay, instead of having my red dotted lines be there at 0.05, I'm going to move them out so that I only reject 5% of the time. So Bonferroni just says, take the number of tests you're actually going to do and divide it by that number. So it actually turns out for my case two, where I was looking at 100 tests and then just picking the most exciting one, if I instead compared it not to 0.05, but to 0.0005, then I would get the correct false positive rate. Now, the Bonferroni method assumes that the tests that you do are all independent of one another, and that may be the case, but many times you might have some correlation among your tests. And so Bonferroni would be a little too restrictive to that. So there are some other methods, which I've called resampling-based methods, that can take into account the correlation, say, among exposures, if there were any. Another approach is to instead control what's called the false discovery rate. That's where you are instead going to control the expected proportion of rejected null hypotheses that are false. That tends to be less stringent than Bonferroni and is just another approach. And then finally, probably the method that you are least familiar with is what I'm calling post-selection inference, which is to actually look at the inferential procedure like the lasso or stepwise selection or something like that, and fix up the p-values after the fact. And it's kind of the same idea that I talked about before of like those red dotted lines, like change those in a way that will reflect the procedure that you performed so that you get the correct false positive rate. The important point here is not that you know exactly how to fix each one of these problems, but to realize that all ways of fixing it depend on you being very frank about all of the analytic procedures that you have done. Okay, you can't like do some at home and then come to your statistician and say, these are the exposures I want to look at. You have to tell me like everything you started with and everything you did. That way we can fix the procedure at the end, or fix the p-values at the end. All right, so in conclusion, we've talked about how selective inference may contribute to the reproducibility crisis. I have tried to convince you that having inflated type 1 error rates can hinder scientific research. It can waste time and money. It can promote ineffective treatments, all of which I claim are bad for science. And that it's important to understand the properties of p-values, not just for statisticians, but also as consumers and producers of research. And in some limited cases, your friendly statistician can help you think through these issues and perhaps correct your p-values. So happy to help. And finally, as is my wont, I do in fact have a musical recap, if you will indulge me. So just a moment. All right, here we go. So many studies can't be verified. What's going wrong? What steps can we take to turn the tide? Robust design of studies would be swell, but also let's do our statistics well. I can go for a pre-specified test, but beware p-values from selective inference. Model selection, better take it slow. Multi-comparisons, I might say, whoa. I'll do anything that passes peer review, yeah, and I'll do almost anything to please reviewer too, yeah, but I can't go for that, no. No can do, I can't go for that, no. No can do, I won't do those stats, no. No can do, I can't go for that, can't go for that, can't go for that, can't go for that. Thank you. So finally, just a couple of acknowledgements: Christine Limonte, David Prince, and my lyricist, Greg Crowther. And finally, I'm happy to take any questions. I hope you are not as fearful as Emma Watson looks in this picture.
Thank you so much, Leila. Everyone, I look forward every year to your musical interludes. So some positive, supportive comments in the chat. Anyone with questions for Dr. Zelnick?
Hey, Leila, it's Alex. I had a question in terms of how practically do you see implementing a lot of these kind of different methods, especially like you show like the Bonferroni or the false discovery rate? Just because one thing I've noticed is that it's kind of rarely implemented in a lot of observational research right now, and you're competing against these people, you know, to make sure you get enough publications or that, you know, they're accepted, and it's and you want to put out the highest quality research. And I guess my question is, you know, how do you see moving forward and trying to improve upon these things within the realistic ecosystem of academics?
Yeah, so it's a great question. And to be honest, I've kind of skated over an important point here, which is to say that, you know, we know that type 1 errors are just sort of baked into statistical inference. And the real question is, where do you want to control the false positives? So they talk about like the family-wise false positive rate, which is to say, like, if I write one paper with all 100 items of my fake instrument in there, do I want to control, you know, that any one of them doesn't have a false positive, or do I want to control that the whole the whole instrument doesn't have at least one false positive. So if the latter is true, if I want to control across the whole instrument, then I think a Bonferroni correction or some kind of correction would be appropriate. But if not, then multiple comparisons might not actually be an issue that you really need to worry about. But I think it's important for people to realize kind of what the issues are and how that might affect, doing lots of tests, both say to come back to a reviewer who says like, why didn't you control for multiple comparisons? You could say, well, these are just like different things that we're interested in. Think about like if you were to split, okay, this is kind of a silly example, but like my instrument, if I were to split that up into 100 different papers, each of which had one exposure and one outcome, like I wouldn't control for multiple comparisons across that. So if each of those are sort of interest, then perhaps I don't want to control across the whole family, but rather just each one individually. So I don't know, that's kind of a subtle point. I totally empathize with what you're saying of that the pressures in publishing and in the academic world are in the wrong direction, right? Because they're trying to encourage you to have a significant result, get lots of publications. But I don't know, I just mostly want to educate people on what are possible downstream effects of these analytic choices.
Yeah, it's really interesting. Thanks so much.
Ian, it looked like you had a question.
Yeah, I had a question. Thanks for seeing my hand, and thanks for waking me up. The song was at least as effective as my coffee this morning. I loved it. Now we're, of course, in the big data era. We have different types of big data being used largely for discovery. We have EHR data that are being mined for prediction models, and in KPMP and other places, we have huge data sets with molecular signatures and things that are being evaluated with the intent to discover new things and lots of possibilities for false positives. So can you comment on that a little bit, apply what you've taught us here to those big data scenarios, which seem even more fraught potentially?
Yeah. So that's really the sort of in follow up to Alex's question, that's really the place where I worry a little bit more of where you really are being very agnostic as to what are the exposures that you're interested in. And I'm just going to look at, 10,000 different variables and then see what pops out. The situation with the EHR, I think, is in some ways worse and in some ways better because, worse, you have lots of predictors, but better in the sense that you have lots and lots of data so that you can, one approach that I didn't put up here, but that would be valid, of course, is to do like sample splitting, of take half of your data, do whatever you want with it, pick out some things that are interesting, and then just go and look at it in the independent data. That will give you correctly sized p-values with your pre-specified hypotheses now in your new data. The other comment I just want to make is that everything that I've talked about here is about p-values, where you're really trying to look at estimates of association or treatment effect if you're thinking about a RCT. If you're in the land of actual true prediction, none of this applies. Okay, because you're not really dealing with p-values at all. You don't really care. Prediction's really kind of a wild west, like whatever works, works. You still do have considerations about like, did the data you developed your model in, is that what you're evaluating it in? Some of those questions, but the p-value multiple comparisons thing doesn't really apply.
Right, well, I have a bunch of questions, but unfortunately we're at the end of the 30 minutes. And Leila, I might pick your brain offline about some other things. Thank you very much for that great talk.